Okay, so I'm going to do an example calculating the electric field due to 2 point charges. So let me draw a diagram. So I'm going to set up first of all an XY coordinate system. There's my y-axis. There's the x-axis, and there's 2 point charges. So Q1, so I'm going to draw it in red, just to, it's at the origin. And then Q2, and so there, the values of those charges. Q1 is 8 nanocoulombs. Q2 is 12 nanocoulombs. Okay, so these 2 charges, point charges, are sitting there, and they're a distance 4 meters apart from each other. Okay, and so what I'm going to do is, so each of those point charges produces or creates its own electric field at every point in space. So, you know, say at this point over here, which we're actually not going to look at, but right there at that spot in space, this is an empty space. It's all empty space except for these 2 point charges. At that point in space, Q1 is producing its own electric field at that spot, which has a magnitude and a direction. And the charge Q2 is also producing its own electric field at that point. And the net electric field at any point in space, it's the vector sum of the individual electric fields at that point in space. Okay, so it's not that point in space that we're going to deal with in this example. So first, part A, find the net electric field at the point x equals 7 meters on the x-axis. Okay, so x equals 7 meters, that's over here somewhere. I'm going to draw an x right there. That's the point. And it's, notice that x equals 7 meters. That's 3 meters away from Q2. Okay, so the net electric field at any point in space, it's the vector sum of the electric field due to charge 1, and I'll just call it E1, plus the electric field due to charge 2, call it E2, at that point in space. So we have to calculate each individual electric field. The electric field due to Q1 at this spot, and the electric field due to Q2 at that point, and add them together as vectors. Okay, and so the best way to do this is, first of all, anytime you're calculating the electric field at some point in space, draw the individual electric field vectors that exist at that point due to each of the charges, if you can, if you know their directions. Okay, and so for a point charge, well, I'm not going to write the formula yet. We just want to know what's the direction of E1 and the direction of E2 at this spot. Well, each of these 2 charges are positive. Okay, these are both positive charges, and so I'll put a plus sign next to each of them just to emphasize that. Okay, so at any point in space, the electric field due to a positive point charge points directly away from that charge. Okay, so there's 2 electric field vectors, and really I should be drawing them with their tails at the spot where we're calculating the electric field, but they're going to be right on top of each other, so I'm going to draw them off to the side a little bit. So at this point, E1 points directly away from Q1. I'll draw it in red. So there's E1. So it's pointing in the positive x direction, so away from Q1. And at that same point in space, the electric field due to Q2, it's a positive charge, so it produces an electric field that's pointing away from it. I'll draw it in black. Right there, E2. But no, I want to emphasize both of these electric field vectors are at the same point in space, which is right on the x-axis. Okay, so really their tails should be drawn right on that point. I drew them a little bit apart from each other just so you can see the 2 electric field vectors. Okay, so how do we calculate this as a vector sum? Well, so the same way that you add vectors anytime, the x component of E It's the sum of the x components, e1x plus e2x, of the individual vectors, e1 and e2. So we have to calculate each of those, e1x, e2x. And then also ey is e1y plus e2y. That's equal to 0 for this case because e1 and e2, they point in the positive x direction. They have no y component. The individual y components are 0 of those two vectors. Okay. Alright, so e1x, well, to calculate the xy components, we need to know the magnitudes of each of these vectors. Okay, so e1, magnitude of e1, this is the formula for the magnitude of the electric field due to one single point charge. So it's K, absolute value of Q1, divided by R1 squared. Where R1 is the distance of this point from the charge Q1. So if I draw that in here, right there, that's R1. Okay, that distance. And this is the point x equals 7 meters, so that's 7 meters from Q1. Okay, so plug in all the numbers. 8.99 times 10 to the 9, that's that K constant, Newton meters squared per coulomb, times the absolute value of Q1, that's 8 times 10 to the minus 9 coulombs, and then divided by the square of the distance of this point from Q1, that's 7 meters squared. And I left off this unit here. This is actually coulomb squared for that K constant. Okay, so the magnitude of E1 is 1.47 newtons per coulomb. So that's the magnitude of the electric field due to charge Q1 at that spot. So what's E1x? Well, you get this just from looking at the picture. E1 is pointing in the positive x direction. So E1x is just equal to the magnitude, E1. So 1.47 newtons per coulomb. Okay. Okay, so what about E2, the electric field due to charge Q2? So the magnitude of E2 is K, absolute value of Q2, over R2 squared. R2 is the distance of this point from charge Q2. So it's that distance right there, R2. And you could see from the picture that's 3 meters. Okay, so this is 8.99. I'm going to leave off units for this one. 10 to the 9. Absolute value of Q2 is 12 times 10 to the minus 9 coulombs, divided by the square of that distance R2, 3 squared. Okay, and so if you plug in the numbers there and calculate it, you get 11.99 newtons per coulomb. So that's the magnitude of E2. So what's its x component? Well, again, E2 is just pointing in the positive x direction. So the x component of E2 is just the magnitude, E2. So 11.99 newtons per coulomb. Okay, so the net electric field at that spot, the x component, is E1x plus E2x. And so that is adding together 1.47 and 11.99. And so that's 13.46 newtons per coulomb. Ey, we already said, was 0 at that point. So then the net electric field written as a vector, E vector, it's 13.46 newtons per coulomb times the unit vector I hat. And that's at x equals 7 meters. Okay. Okay, so the net electric field points in the positive x direction. That's obvious because the two vectors that were the two individual electric field vectors, they both point in the positive x direction. So when you add them together, the net field points in the positive x direction also. Okay, so now let's calculate the net electric field at a different point on the x-axis, E. This one's in between the two charges, and so this is at x equals 3 meters. And let me redraw the diagram down here. So here's Q1, here's Q2. 4 meters is this distance. This is my x-axis, positive x-axis. X equals 3 meters, that's like right here. Okay. So that's the spot on the x-axis that we want to calculate the electric field, the net electric field. Okay, so same equation to start with. The net electric field at that point, it's the vector sum of the two electric fields due to each individual charge. So let me draw each of those. That's the first step. Before you calculate anything, draw the electric field vectors at this point where we're trying to calculate it. So, and again, these are both positive charges. So this one's positive, that one's positive. So E1, I'll draw it in red like I did before. E1 at this spot points directly away from the charge Q1. And so it points, actually I'll draw them right on the x-axis. So there's E1. Okay, it points to the right at that spot. What about the field due to Q2 at this point? Well, this is a positive charge, so the field due to that one charge points directly away from it because it's positive. So that field, E2, points to the left at that spot. Okay, so the two electric fields that we have to add together as vectors, one of them points to the right, one of them points to the left. Okay, but we go through the same procedure as before, and I'll skip a few steps here. Again, what's the magnitude of E1? So it's going to involve the distance of that point from charge Q1, and so that's R1, that's 3 meters in this case. And then R2, which is the distance of this point from charge Q2, that's what enters into the formula for E2. That, as you can see, that's 1 meter. Okay, so using the same formula for E1 and for E2, just different distances in there now. The magnitude of E1 at that spot is 7.99 newtons per coulomb. The magnitude of E2 is 107.88 newtons per coulomb. Okay, so those are the two magnitudes. Then we need the x components of each of them, because again, the x component of the net field is going to be obtained by adding together the x components of the two individual fields at that spot. So E1x, E1 points in the positive x direction, so it's just equal to the magnitude E1, which is 7.99 newtons per coulomb. E2x, the x component of the electric field due to Q2, you can see it's pointing to the left, which is the negative x direction. So E2x is going to be minus the magnitude E2. So it's minus 107.88 newtons per coulomb. Notice the x component of E2 is negative, even though the charge Q2 is positive. Yeah, so I mean, the fact that the charge is positive doesn't tell you anything about the sign of the component of its electric field at any arbitrary point. Yeah, they don't like go together. Just because the charge is positive doesn't mean that it produces a positive electric field. Doesn't mean that it produces a negative electric field. The x and y components of its electric field at a given point in space depend on the point in space that you're talking about. Okay? So Ex here, the net field, it's E1x plus E2x. So adding those two together, you get negative 99.89 newtons per coulomb. And again, Ey here is 0 because these two vectors don't have any y components. So then finally the electric field, the net electric field at that spot, written as a vector, the x component is this negative 99.89, so it's minus 99.89 newtons per coulomb and then I hat, the unit vector I hat. Okay, so the net electric field at this spot, if I draw it again just to make it a little clearer, here's Q1, here's Q2, and then the point in space that we were calculating the electric field. The net electric field at that location points directly to the left in the negative x direction. So there's the net electric field.